In this video, we will be discussing the two popularly used spanning tree algorithms, Prim's algorithm and Kruskal's algorithm. But before diving into those algorithms, let's try to understand what a spanning tree is. And in order to understand what a spanning tree is, we need to first understand what exactly is a subgraph. So you can go through the definition, just pause the video and go through the definition of subgraph. So I hope you have gone through the definition of subgraph. I'll try to summarize it for you. See, given a graph, I'll explain it with the help of this example. So here you see a graph denoted by the name of G, which has how many vertices? A, B, C, D and E. There are 5 vertices and there are 1, 2, 3, 4, 5 edges. 1, 2, 3, 4, 5. 5 vertices and 5 edges. Now, such a graph which has been given to you, from this graph what you can generate are subgraphs. Now what will a subgraph look like? A subgraph will contain a few of the vertices of the original graph. So here you have 5 vertices. So from the 5 vertices, let's say you decide to take the vertices A, B, C and D. You decide to take 4 vertices. Now if you include these 4 vertices, you need to include the edges that are connecting them. So I'm including A, B, C and D. So A and B is connected by the edge which has a weight of 1. So I need to include that edge. In my original graph, the vertices B and C are connected by the edge which has a weight 2. So I need to include that edge. Similarly, in my original graph, the edge or the vertices C and D are connected by the edge which has a weight 3. So we have to include that edge as well. Now, since the vertex E is not included, we do not need the edge connecting A and E, and we also do not need the edge connecting D and E because the vertex E is not present in our subgraph. Another subgraph could be G double dashed. Now in G double dashed, what we decide to do is we include the vertices A, B, C, D and E. Now here you can see that all 5 vertices have been included, but we have not included the edge between C and D. The edge connecting C and D, which has a weight of 3 in the original graph, is not included in my subgraph. This is perfectly alright. A subgraph will be such that it contains a few of the vertices and all edges which are connecting the vertices such that there is no disconnection in my graph. What do you mean by disconnection? In order to understand disconnection, let's try to understand what do you mean by a connected graph. See, in a connected graph, there will be a path from one vertex to all other vertices. So if I start from vertex D, although I have not included the edge from D to C, I can still reach the vertex C starting from vertex D. How? I can go from vertex D to E, followed by vertex A, followed by vertex B, followed by vertex C. So in this way, what can happen is you can still start from any vertex and reach any other vertex. As a result, this subgraph that you see, G double dashed, is still connected. And as a result, we can do away with this edge. You can also have the edge. Even if I had this edge connecting C and D, it would still have been a subgraph. Anyway, now with the concept of subgraph clear to you, let's try to understand what a spanning tree is. Again, you just pause the video and go through the definition of spanning tree. So I hope you have gone through the definition of spanning tree. Let me again summarize things for you. For a graph to be a spanning tree, see, you will be given an original graph like you have been given here, graph G. From that, you have to generate spanning trees. Now, what are the conditions that need to be satisfied for a graph to be a spanning tree? See, a spanning tree will always be a subgraph. As you can see, it has been mentioned that it is a subgraph of the original graph G and is denoted by capital T. And capital T also has a vertex set and an edge set, which are subsets of the original vertex set and original edge set. So 3 conditions have to be satisfied. The vertex set of my subgraph should be same as my vertex set of the original graph. So you can see that the vertex set of my subgraph T is V dashed. Now the content of V dashed has to be same as the content of V. That means all the vertices which are present in the original graph must also be present in my spanning tree, which is a subgraph. Okay, remember, spanning tree, the first condition for a graph to be a spanning tree is that it has to be a subgraph. So in the subgraph, all vertices of the original graph must be present. That's point number 1, which has been shown here. Point number 2 is the subgraph which you are getting has to be a connected graph. Just now I explained what a connected graph is. If you are able to start at any vertex and reach any other vertex in the graph is said to be connected. So the graph has to be connected. Okay, for a spanning tree to be formed, it has to be a connected graph. And the third point is it has to be acyclic. What do you mean by acyclic? Acyclic means the absence of cycles. Now, what is a cycle? A cycle is a path where the starting vertex and the ending vertex happen to be the same. That means you start at one particular vertex and you come back to the same vertex after visiting all the edges exactly once. So such cycles will not be allowed in our spanning tree. So if you have a subgraph which satisfies all the 3 conditions that has been mentioned here, that is the vertex, all the vertices present in the original graph must be present in the subgraph. The subgraph has to be connected and the subgraph has to be acyclic. If all these 3 conditions are satisfied, then we say that the subgraph is a spanning tree. So I hope this definition is understood. Now let's move on. If you have understood spanning tree, now you are in a position to understand what a minimum spanning tree is. Generally, when you will be asked to apply Prim's algorithm or Kruskal's algorithm, the graph that will be given to you will be a weighted graph. And what is a weighted graph? A weighted graph is a graph in which every edge carries a number which denotes the weight of the graph. And a minimum spanning tree, in order to define a minimum spanning tree, our edges have to be weighted. That is what you mean by edge weighted. It has to be undirected. That means every edge will be read in the same way from both ends. That means this edge which you see, which has a weight of 12, you can identify this edge as V3, V4 as well as V4, V3. So the order of the vertices will not matter in an undirected graph. And it also has to be a connected graph. So your minimum spanning tree, whenever you're trying to define the minimum spanning tree, the graph has to be connected. So such a spanning tree which will have a minimum total cost. That means if you take up the sum of the weights of all the edges of your spanning tree, the spanning tree which has the minimum sum of weights will be called the minimum spanning tree. So here from graph G, you can see graph G is a graph which has 4 vertices and 4 edges. Now all the edges have been numbered. Each number represents a weight of the edge. Now here what you can see is, since all the edges are connected with each other, we can say that, or let's say all the vertices are connected with each other, we can say that this is a connected graph. Now from this connected graph, you can generate 4 spanning trees. Like you can see here, see, T1 is a spanning tree. Why? Because there is no cycle. All the vertices present in G are also present in T1. And also, if you remember, T1 is connected. So these are the 3 conditions for a graph to be a spanning tree. If you remember from the spanning tree definition, we had listed out 3 conditions for a spanning tree, for a subgraph to be a spanning tree. The first condition was that all the vertices present in the original graph must be present in the subgraph. The second condition was the graph has to be connected. And the third condition was it has to be acyclic. Now since all the 3 conditions are satisfied for T1, T2, T3 as well as T4, you can see in all these 4 cases there is no cycle in the graph. There is no cycle in the graph, as well as all the graphs are connected and all the vertices are present in T1, T2, T3 and T4. See, graph G has 4 vertices. Graphs T1, T2, T3 and T4, all of them have 4 vertices as well. Although I have not labeled them, you can probably understand that. Okay, I'll just label it for you. As you can see, all the vertices have been labeled. So all the vertices present in the original graph G are also present in my subgraphs. All the subgraphs are connected. That means starting at a particular vertex, you can reach any other vertex. And also, none of these subgraphs, T1, T2, T3, T4, contain a cycle. As a result, we can say that all of these subgraphs are spanning trees. Now the question is, which of these is the minimum spanning tree? If you observe, if you take the sum of the weights, if you take the sum of the weights of T1, what will you get? 10 plus 20, that is 30. 30 plus 12 is 42. So T1 has a sum of weights as 42. Similarly, if you take up the sum of weights of T2, you will get 10 plus 36, 46. 46 plus 12 as 58. Similarly, if you take the sum of weights of T3 and T4, and if you compare all the four, you will find that graph T1 has the minimum sum of weights, which is 42. As a result, we'll say that out of these four spanning trees, T1 is the minimum spanning tree. Okay, so for every graph, you will be having one minimum spanning tree. Now, by one minimum spanning tree, what I mean is there will be the sum of weights. The sum of weights will be exactly one value, no matter what kind of graph it is, no matter whether there is any repetition in the edge weights or not. The sum of weights of the minimum spanning tree of your graph will always be one unique value. Okay, so just keep these points in mind. Now let's quickly go through these remaining points. So remember, to find the minimum spanning tree, we may use either Prim's algorithm or Kruskal's algorithm. Both will be used to find, or you can use, what I mean is you can use any one of them to find the minimum spanning tree. And remember, if your edge weights, if the weight of every edge in your graph is unique, that means all the edge weights are different, then the minimum spanning tree is also unique and the total cost is also unique. But if your edge weights are repeated, that means if you have something like this, let me show you a diagram. What I mean is, by edge weights being repeated, let's say you have a graph like this. Let me show it here. Let's say you have such a graph. Now, let's say it's like this. Okay, so if edge weights are repeated, now this is a very trivial graph, but I think you can understand what I mean by edge weights being repeated. You can see that this edge and this edge, they have the same weight of 1. Now if such edge weights repeat in a graph, if edge weights are found to be repeated in a graph, then the total cost will be unique. The total cost is always unique, but the minimum spanning tree may or may not be unique. Okay, the minimum spanning tree may or may not be unique. I think you can understand this even better if I have a graph in which all edge weights are same. Let's say this is, instead of being 2, this is 1, and instead of being 3, this is 1. Okay, if all edge weights are exactly 1, you can understand that. See, from this graph, what are the spanning trees you will get? You will get the spanning trees in exactly this form: T1, T2, T3, T4. These are the 4 possible spanning trees you get from this graph. Okay, that is understood. But now the question is, all 4 of them will qualify as minimum spanning trees, because from this graph, what will you get? You will get this as a spanning tree, you will get this as a spanning tree, you will get this as a spanning tree, and you will get this one as a spanning tree. Now, since all edge weights have a same value of 1, what happens is, see, all edge weights have a same value of 1. So all of these have a minimum sum of weight as 3. So the minimum sum of weight remains unchanged, but the minimum spanning tree varies. Okay, so this is the point that I was trying to make, that if edge weights are repeated, the minimum spanning tree may differ depending on the algorithm we are using, but the total cost, like you can see here, the sum of weights in all the 4 cases is 3. The total cost will always remain the same. Okay. One more point you must notice, point number 7, that the graph must be connected in order to find the minimum spanning tree. So if you have a graph which is disconnected, what could be a disconnected graph? A disconnected graph could be something like this. Let's say you have a graph like this. Let's say this is one complete graph G. Now if you consider this graph, how many vertices are there? There is 1, 2, 3, 4. There are 4 vertices. 1, 2. Total of 6 vertices. There are 2 components. This is one component. This is this is the second component. There are 2 components in this graph. There are 6 vertices in total. Now all these vertices are not connected. You cannot apply either Prim's algorithm or Kruskal's algorithm to such a graph to find the minimum spanning tree. Okay, so the graph must be connected if you have to find the minimum spanning tree by applying either Prim's algorithm or Kruskal's algorithm. Remember, every minimum spanning tree must contain min e. What is this min e? Min e refers to the edge weight having minimum value. So min e is your edge weight is your edge weight with minimum value. With minimum value. That is min E. Similarly, you can have max E. So what would be max E? So max E would be edge weight with maximum value. Now here, if you observe in this graph, what is your min E? In this graph, your min E is 10. Your min E is 10. Why? Because it is the edge having the least possible weight. And what is max E? Max E is this edge having the maximum value of 36. So remember, every minimum spanning tree will always contain the min E, will always contain the edge having the minimum value. Remember this, every minimum spanning tree will always contain the edge having the least weight, having the minimum value. Okay, just keep that in mind. I hope you have understood what is min E and max E. Min E is the edge weight with minimum value. Max E is the edge weight with maximum value. Every minimum spanning tree will always contain the edge having the least weight, having the minimum value. Because in both the algorithms, in Prim's algorithm as well as Kruskal's algorithm, will always start with the edge having the least weight. And what is point number 9 telling us? Point number 9 is telling us that a minimum spanning tree will contain the edge with the maximum weight only when its removal will disconnect the graph. That means if you have a graph, let's say somewhat like this. Let's say you have a graph like this. And let's say this edge has a weight of 100. And let's say the remaining weights are 2, 3, 4, this is 5, this is 1, this is 7, this is 8, and this is 9. Now you can see that the edge which has the maximum value is 100. And this edge happens to be acting like a bridge between this part of the graph as well as this part of the graph. So you have no other choice but to always include this edge. You have to, because if you do not include this edge, then your graph will become disconnected. So this is what you mean by the last point, that the edge having the maximum weight will be included in your minimum spanning tree only when its exclusion will disconnect the graph. That means if I do not include this edge having a weight of 100, if I do not include this, then this entire graph becomes disconnected. As a result, this is the only scenario, or this is, this represents one of those cases where removal of an edge which has the maximum weight happens to disconnect the graph. Okay, so I hope these points are understood. Next, what we'll do is we'll move on to the algorithms. Let's try to apply Prim's algorithm on the given graph to find the minimum spanning tree. So how would you go about it? I'll show it step by step. What you can do is you can just go through these points. This just summarizes the steps that we need to follow in order to find the minimum spanning tree. And one more thing that you need to observe is every edge weight in this graph has a unique value. So the minimum spanning tree that you will get is unique. For this graph, you will get only one copy of the minimum spanning tree. Whether you apply Prim's algorithm or Kruskal's algorithm, it will not make any difference. Okay, so let's start. Okay, so what I'll do is I'll just tilt this a bit so that it's easier for me to write. So what will be my step 1? My step 1 will be to find the edge having the least weight. So which is the edge having the least weight? The edge having the least weight, if you observe closely, is this one. Okay, I'll mark it with this red color. Let me mark it with the red color. So this is my edge with the least weight. Now what I'll do is I'll include this weight. I'll include this edge. Now including this edge means including the vertices associated with the edge. So I'll include the two vertices 6 and 1, and I'll also include the edge weight, which is 10. This is step number 1. So I hope you can write it in your own words. So what the reason for including this edge? Because it is the edge having the least weight, right? Okay. Now, one more thing is, what is the stopping condition? When will you stop adding edges? When will you stop looking for edges? You will stop looking for edges once you have added n minus 1 edges, where n denotes the number of vertices. This is important. N denotes the number of vertices. So how many vertices are present in this graph? You can see that there are 1, 2, 3, 1, Where is 2? Yeah, 1, 2, 3, 4, 5, 6, 7. So there are 7 vertices in this graph. We'll keep on iterating over this graph till the time we have added how many edges? 6 edges in this case, because there are 7 vertices. Here n is 7. So we'll keep on adding edges till we have added 6 edges. Okay. So this is step 1. So you can write it in your own words, the reason for this, for me including this edge. Now, from here onwards, please pay very close attention. I have vertices 1 and 6. Now, which are the edges I'll consider? I'll consider only the edges that are incident on the vertices 1 and 6. I'll not look at the entire graph now. The initial step involved looking at the entire graph to find the edge having the minimum weight. But from then onwards, what I'll do is I'll consider only those edges which are incident on the vertices that are currently in my minimum spanning tree. In my minimum spanning tree, I can see that there are only vertices 1 and 6. So I'll consider the edges that are incident on the vertices 1 and 6. So which are the edges incident on 1 and 6? I can see that on the vertex 1, I have this edge. I have this edge having a weight of 28. I also have, of course, I'm not going to include this edge again. This has already been included. This one has already been included, so I'll not be considering it anymore. I have this one edge having a weight of 28. I have this edge having a weight of 25. Right? Do I have any more edges incident on 1 and 6? No. See, 1 had this edge and this edge. 6 had this edge and this edge. So 1 and 6 had one common edge which we have added. Other than that, there is this edge for 1 and there is this edge for 6. So out of these two, out of this edge having a weight of 25 and this edge having a weight of 28, which one has a lower value? I can see that 25 has a lower value. So I will choose the edge having a lower value. That means I'll choose this edge. So I'll choose this edge and add the weight 25. So this is my step 2. This is my step 2. Due to shortage of space, I'll not be drawing the diagram at every step, but what I would suggest you to do is, for your examination purpose, please draw the diagrams separately for every step. And one more thing that you must keep in mind is, we do not have to check for cycles. Why is it so important to check for cycles? Remember, the spanning tree must not include a cycle. As a result, it may be required for us to check for cycles at every step. But Prim's algorithm is one such spanning tree algorithm which does not require the checking of cycles. So we do not have to worry about cycles in this case. Okay. Now we have the vertices 1, 5 and 6. Okay, I'll just show step 3 separately so that you can understand what I'm talking about. And for every step when you're choosing an edge, give the reason which I'm explaining in my words. So you can pause the video from time to time and make your running notes. So in step 3, I can see that what are the vertices included in my graph? In my graph, I have the vertices 1, 5 and 6. So I'll consider only those edges which are incident on 1, 5 or 6. So I can see that this edge is under consideration, the one which has a weight of 28. The edge which will not consider any further is this one, because this is already done. It's already been included. Now, what else? On vertex 6, there is no other edge which has not been included. See, vertex 6 had this edge of weight 10 and this edge of 25, and we have included both of them in our minimum spanning tree. So we cannot consider them any further. Now the new vertex that we have added is 5, and the two edges that it brings into the picture are this one having a weight of 24, the edge having a weight of 24 comes into the picture, and the edge having a weight of 22 comes into the picture. Now, how many edges are we considering? We are considering the edge with 22, the edge with 24, and the edge with 28 weight. So out of the 3, which is the least cost? Out of the 3, we can see that 22 has the lowest value, so we will include that edge. So in the process of including the edge, we end up including the vertex 4. So what we'll do is, I'll just redraw the diagram. So I have 6, I have 1, I have 5, and it also brings into the picture vertex 4. And it has a weight of 22. Okay. Now this had a weight of 25, this had a weight of 10. So far we have included 1, 2, 3 edges, right? Fine. Now which are the edges that we'll consider? Okay. Which edge is no longer under consideration? This one. This one is done and dusted. Now, the edges that we need to consider are this one of vertex 4 coming out from vertex 4. This edge is under consideration, of course. This edge is also under consideration. And what else? What about vertex 5? Vertex 5 has an edge of 24, which is under consideration. And what else? And yes, the edge which we have been considering for the last couple of steps, the edge between 1 and 2, that is also there, a weight of 28. Now, out of these 4 vertices, out of these 4 edges, 1, 2, 3, and 4. Out of these 4 edges, which has the least weight? This one has the least weight, right? So we will include it. So we will include it in our minimum spanning tree. So we'll include the vertex 3 and it has a weight of 12. So this one has been included, right? Now, since 3 comes into the picture, what are the edges that it brings along? It brings along the edge 16. So out of now the edges that we are considering are this edge 16, this edge 28, this edge 18. Any other edge are we considering? I guess not, because 3 has brought along a new edge which has a weight of 16. 4 already has an unincluded edge which has a weight of 18, and the edge from 1 to 2 is still there. The edges coming out from 5 are 25, 22 and 24, and this edge is still there. But out of these edges, out of 25, 18, 16 and 28, the least weight is that of 16. So we will include it. So we'll include 16. So this part is now included. So I'll just cross it out for your convenience so that you can understand. And I'll include the vertex 2. So I'll include the vertex 2 and I'll have the weight 16. I'll have the weight 16. Okay. Now with vertex 2, what you have is now the edge 14. Now what are the edges that you will consider? You'll consider the edge 18. The edge 14 has come into the picture because it is incident on our newly added vertex 2. The edge 24 comes into the picture and the edge 28 is also there. So out of 28, 14, 18 and 24, 14 has the least weight, so we'll add it. So we'll add this edge from 2 to 7. So we'll add it from 2 to 7, right? Now what is the weight of this edge from 2 to 7? The weight is, if you observe, it's 14. So 14 is the weight. So how many edges have we added? We have added 1, 2, 3, 4, 5, 6, right? See, 1, 2, 3, 4, 5, 6. So we have added 6 edges. And how many edges were we supposed to add? We were supposed to add n minus 1 edges. What is the value of n? 7. So how many edges we can add at max to form a minimum spanning tree? We can add 6 edges, and we have successfully added 6 edges in our spanning tree. So this gives us the minimum spanning tree. So what is the total cost? Our job is not over. We have to find out the total cost. So we have to find out the total cost of the minimum spanning tree. So what is the total cost? You simply sum up the edge weights. So that is 10 plus 12 plus 14 plus 16 plus 22 plus 25. So if you sum up these values, what will you get? You will get 10 plus 12 as 22, 36, 52, 54 plus 22 is 74, and here you will get 25. So what do you get? Would you get the value? Let me just calculate. So if you calculate, you end up getting 99. Okay, so this is the total cost of the minimum spanning tree, and this is the minimum spanning tree that you get. So this is how you can apply Prim's algorithm to get your minimum spanning tree. Now we'll apply Kruskal's algorithm on the same graph and see what is the result. If our method on Prim's happens to be correct, and if the method which I am about to show you on Kruskal's algorithm happens to be correct, we'll get the exact same result for the minimum spanning tree as well as the total cost. Because the edge weights, mind you, are unique. Since the edge weights are unique, the total minimum cost will be unique, definitely. And along with that, the minimum spanning tree structure will also be unique. So let's see how we can apply Kruskal's algorithm. So this is Kruskal's algorithm. Now this is slightly different. In Prim's algorithm, we kept on adding edges and vertices. Of course, we added both, but we did not require to check for cycles. Here what we'll do is, here we'll assume, so in Prim's algorithm we were adding edges and that brought along new vertices, but here we'll assume all vertices to be present in our graph at every step, and we'll keep on adding the edges in ascending order, okay, or let's say in non-decreasing order. We'll keep on adding edges in non-decreasing order. By non-decreasing order, what you mean is either the edge weights will increase from a smaller value to a larger value, or it will remain the same. That is the meaning of non-decreasing order. Okay, so let's see how we can go about it. So in every step, you'll assume all the vertices to be present. So again, I'll just iterate over one graph, but you have to show the separate steps for your examination, and you'll have to write the reason, which I'm explaining in my own words. I hope you're pausing the video and noting down the required points, because you'll have to write the reason for including an edge at every step. So let me just list out the vertices. So this is 3, this is vertex 4, this is vertex 5. And another difference between Prim's and Kruskal's is that in Prim's algorithm we didn't require the checking of cycles, but here we have to check for the presence of cycles. Okay, fine. Now let's see. Let's look at the edge which has the least weight. Which is the edge which has the least weight? This one. The edge between 1 and 6. Right? The edge connecting 1 and 6 has the least weight. So we will include it in our graph. But before including, we'll check whether the inclusion of this edge will lead to a cycle or not. So if I include this edge, is it leading to any cycle? Of course not. So I can include it in my graph. Next, what I'll do is I'll look at the edge weight having the next higher value. So after 10, which is the edge weight having a higher value? Like, which is the edge weight which is greater than 10 but closest to it? So which is greater than 10 and closest to it? 12. 12 is greater than 10 and it is closest to 10. So I'll add this edge. Okay, I'll add the edges in increasing order, in ascending order of weights. Either the edge weights will be in ascending order or they'll remain the same. So after 12, the next higher value is, after 10, the next higher value is 12. So I need to add that edge. But before adding, I need to check. If I add this edge, will it lead to any cycle? Of course not. So I can add it. So I'll add this edge and its weight is 12. That's fine. Now remember, while forming this minimum spanning tree using Kruskal's algorithm, you will end up getting a disconnected graph at the intermediate steps. Like this is, I think I'm at step 2. So at step 2, I can see that this graph is disconnected. But that's fine. At the end of the procedure, you will come up with a connected graph. Okay, so there's nothing to panic about. You just keep on adding the edges in non-decreasing order of weights and check for cycles. Now, after 12, which is the edge having the next higher value? So after 12, you have this edge having a weight of 14. So let me add it. So if I add it, will it lead to a cycle? Of course not. So I'll add it. Okay. Now followed after 14, which is the next edge weight that I should consider? The edge weight that I should consider is 16, the edge between 2 and 3. So if I add this edge, will it lead to a cycle? Of course not. So let me add it. So that was, I think, step number 4, I guess. So yeah, I'm at step number 4. And next, what should I do? I should look for the edge having the next higher value after 16. After 16, the next higher value is 18, the edge connecting 4 and 7. But if I include 18, it will lead to a cycle. See, if I include 18, if I include this edge, you can imagine that this complete pattern will be, this pattern will be completed and it will lead to a cycle. So I cannot add this edge. I cannot add the edge connecting 4 and 7. Okay, I'll have to look at the next edge. So after 18, which is the next edge that I have? After 18, I have, I think, 22. So if I add 22, will it lead to a cycle? No, it won't. So let me add 22. So I'll add 22. Now after this, the next edge that I should consider is 24. So 24 connects 5 and 7. But if I add this edge, it will lead to a complete cycle. And which vertices will it involve? It will involve a cycle consisting of the vertices 2, 3, 4, 5, 7, 2. So if I include this edge here, then I get this closed figure, and a closed figure will lead to a cycle. That's why I cannot include this edge. I'll have to look for the next edge. So which is the next edge after 24? After 24, the next edge is 25. Now, if I add this edge 25, will it lead to a cycle? Of course not. So let me add it. So let me add the edge 25. Now, which is the next edge that I should be looking at? I should be looking at the edge 28. Now, if I add this edge 28, I'll get a closed figure. What is the closed figure? 1, 2, 3, 4, 5, 6, 1. So starting from 1, I can again come back to 1. So it will lead to a cycle. That's why I cannot add this edge 28. Now, if you have observed that I have checked for every edge once, that's why I can stop my procedure and conclude that this is my minimum spanning tree. Now, if you look at this minimum spanning tree, just pause the video and have a look at this minimum spanning tree. Now, look at the spanning tree that I got using prims. It's exactly the same. It is exactly the same. See, I have the edges 10, 25, 22, 12, 16 and 14. And here also, I have the edges 10, 25, 22, 12, 16, 14. Okay, so this is possible because all the edge weights are unique. Since all the edge weights are unique, the minimum spanning tree is also unique, whether you apply Prim's algorithm or Kruskal's algorithm. Now, if you find the total cost, you will get the same result. So, if you find the total cost of your minimum spanning tree, what will it come out to be? It will come out to be 10 plus 12 plus 14 plus 16 plus 22 plus 25. So what's this total value? 10 plus 12 is 22, 22 plus 14 is 36, 36 plus 16 is 52, 52 plus 22 is 74, 74 plus 25 is 99. So you got 99 here and you got 99 here as well for Prim's algorithm. Okay, so the stopping condition for Prim's algorithm was you keep on adding edges till you have added n minus 1 edges, and here the stopping condition was you keep on adding edges till you have checked for every edge once. Okay, so I hope you have understood this example on Kruskal's algorithm. Let's see what we can do next. Let's look at this example. So we have been asked to obtain the minimum spanning tree using Kruskal's algorithm for the given graph. Again, we'll do the same thing. So I'll do it on a single graph, but for your examination purpose, you have to show the steps separately. So you have to show the diagram for every step and write the reason for including an edge. Okay, which I am explaining in my own words as I am solving this question. So you will have all the vertices of your graph at every step. So let me just draw the vertices for you. Okay, now we have the vertices with us. So what we'll do is we'll start with the edge having the least weight and keep on adding edges and check for cycles. We'll add an edge provided it does not lead to a cycle. So which is the edge with the least weight? The edge with the least weight, if you observe carefully, is the edge connecting D and E, which has a weight of 25. So we'll include it, of course, because it does not lead to a cycle. So I'll include this edge having a weight of 25. So that's done. Now, the next highest edge weight is, if you observe, the next highest edge weight is, I think it's 35, right? Yeah, it's pretty sure, I'm pretty sure that it's 35. Yeah, it's 35. So if I add this edge connecting B and D, it will not lead to a cycle, so I can add it. So I'll say 35. Okay, the next edge weight that I'll consider is, the next value of edge weight that I should consider is 42. Observe carefully, it's 42. So if I include this edge connecting H and I having an edge weight of 42, it will not lead to a cycle, so I can include it. Now after 42, the next edge that I should be visiting is 43. Now if I add this edge 43, I get a closed figure. What is the closed figure? BDEB or EDBE. So this closed figure will lead to a cycle, so I cannot add this edge 43. I cannot add this edge 43. So 43 cannot be added in my minimum spanning tree. So what I'll do is I'll just cross it out so that you can understand that it has not been included. Fine. Okay. Now the next edge that I should consider is 45. If you observe, yes, 45 is the one. So if I include 45, it will not lead to a cycle. So let me include the edge 45. Okay, I've included the edge 45. Now the next edge weight that I should consider is 50. See, the next highest weight that I should consider is 50. And if I add 50, it will not lead to a cycle. So let me add 50. Okay. Now, the next edge weight that I should consider after 50 is, which one is it? I think it's 65, right? Yeah, it is 65. So if I include this edge connecting A and C, 65, it will not lead to a cycle. So let me include it as a weight of 65. Now after this, the next edge weight to consider is 70. Is it 70? Let me just cross check. Yeah, it is 70. So if I add 70, it will not lead to a cycle. So I'll add it. So I'll add 70. Now followed by 70, the edge that I should consider is 75. Is 75. Now if I add 75, this is the one connecting 70. This is the edge for 75. If I add 75, will it lead to a closed figure? I guess not. No. There will be no closed figure because of adding this edge 75. Right? Okay. So 75 can be added without having a cycle in our graph. Now after 75, which is the edge that I should consider? I should consider, see, there are two edges. There is an edge having weight 80 and there is another edge having a weight 80. So I have these two edges into consideration. I have this edge connecting vertices F and I. If I include this edge, it will lead to a closed figure C, G, E, C, G, I, F, C. So to avoid this closed figure leading to a cycle, I cannot include this edge of 80. So this edge of 80 cannot be included because it will lead to a cycle. Okay. The next edge that I have is this one, 80. Can I include this edge, 80? If I include this edge, again, it will lead to a closed figure. The closed figure will be A, C, G, I, H, D, B, A. This border, the vertices making up the border of this figure will form a closed figure. As a result, it will lead to a cycle. So I cannot include this edge either. So I cannot include the edge having a weight 80. Now, one thing that you must have observed is, so I have got my spanning tree. That's fair enough. That's done. But one thing you must have observed is, out of all the edges in my graph, which is the edge having the highest weight? Just have a look. The edge with weight 80 has the highest weight. The edge with weight 80 is the highest. As a result, what did I say earlier on in the video? I had said that we will include the edge with the maximum weight only when its exclusion will lead to disconnecting the graph. But if I exclude the edge with weight 80, it is not disconnecting my graph, and as a result, in the minimum spanning tree, it is not included. Okay, so I hope you have understood this. Now, our job is still not over. We have to find the total cost. So we'll write the total cost of minimum spanning tree. The total cost of minimum spanning tree will be the sum of the weights. So what are the weights that we have? We have 25 plus 35 plus, I think, 42, followed by 50, followed by 45, there is a 45 as well, followed by 65, and there is 70. Have I included everything? 1, 2, 3, 4, 5, 6, 7. Are there 7 edges? 1, 2, 3, 4, 5, 6, 7, 8. Are there 8 edges? Am I missing something? Okay, I have included 25. I have included this. I have included 35. So I have included this as well. I have included 42. So I have included this. I have included 50. So this is done. Okay, I missed 75, I think. Yeah. So I have included 65. Yes. I have included 70. Yes. I have included 45. Have I included 45? Yes, I have included 45. But I have missed 75. So let me just add 75. Now, if you add up these edge weights, what will you get? Just add it up. If my calculation is all correct, it comes out to be 407. Okay, you just verify this. Now, we'll take up another example. So let's take up another example on Kruskal's algorithm. Now again, here we have a few vertices and edges. So like previously, we'll have all the vertices of our graph at every step. So I'll just draw the vertices for you. Okay. At every step, we will have all the vertices. Again, I request you to please draw the graph at every step. As and when you're adding edges, please draw the graph separately. Okay. Please draw the graph separately. Otherwise, marks will be deducted in your examination. Okay, so, and of course, include the reason for having an edge in your graph. As and when I'm explaining, I'm telling you the reason why I'm including an edge and why I'm not including an edge. So you need to list out these details as well. See, if I draw the graph separately at every step, it will take up a lot of time and it will be an unnecessary wastage of time. And I don't want that. I want you to understand the concepts at a very fast rate. As it is, this video is getting a bit longer, but I think you can pick up the intuition, and that is very important. And for your examination purposes, I'm telling you what to do. I'm giving you the instructions. You please follow them. And while seeing this video, you make your notes accordingly. You draw the graph at every step. Fine. Now coming back, what we do, we look at the edge having the least weight. Which is the edge having the least weight? The edge having the least weight is the edge connecting E and G. So, and if I include this edge in my graph, it will not lead to a cycle. So I'll include it. And its weight is 2. Okay, next step, step 2. So this, now step 2, the graph will be such that I'll have to include the edge which has a value which is greater than 2 but closest to it. Which is the edge having a value greater than 2 and closest to it? This edge. The edge connecting B and E has a value greater than 2 and is closest to it. So I'll include this. And including it will not lead to a cycle. So I'll include it. Now the next edge that I'll consider is, the next highest edge weight is the edge connecting E and F. So step number 3, I'll have this edge. Now including this edge will not lead to a cycle, so I'll have it. Now the next edge to consider is the edge connecting B and C. Now the edge connecting B and C. So this is my step 4. Now for step 4, the edge connecting B and C, we can include it, right? Because it will not lead to a cycle. So we'll include it. Now next step, step number 5. Step number 5, we have to consider the edge with the next highest value, that is 6. Now if I include this edge, it will not lead to a cycle. So I'll include it. Now step 6. Step 6, which edge do we consider? We'll consider the edge connecting A and D. If I include this edge, it will not lead to a cycle. So I'll include it. Now the next step to consider is step number 7. In step number 7, the edge that we should consider is this edge connecting C and F. But if I include this edge, it will lead to a cycle. So I cannot include this edge. Okay, so you please write down the reason. The next edge to consider is the edge connecting F and I. If I include this edge connecting F and I, it will not lead to a cycle. So I'll include it. I'll include this edge and I'll move on to the next step. So my step 8, I think this will be step 9. At step 8, we decided against the inclusion of the edge 8. Okay, so now step 9, we included the edge weight 9. Now next step is my step 10. Now the edge to consider is the edge connecting H and I. Now if I include this edge H and I, it will not lead to a cycle. It will not lead to a closed figure. So I'll include it. I'll include this edge. Fine. Now the next edge that I should consider is, you please keep track of the step numbers. If I miss out any step number, you please make the necessary changes. Now the next edge to consider is the edge with the next highest value, which is 11. Now if I include this, it will lead to a closed figure, this closed figure, right? EFHI, this EFIHE, this will lead to a closed figure, so I'll not include this edge. Now, the next step, step 12, the edge to consider is this one, connecting A and B. But if I include it, it will lead to this closed figure, A, B, E, G, A, D. See, A, B, E, G, D, A. This will lead to this closed figure. That's why I cannot include this vertex. I mean this edge. I cannot include this edge. I couldn't include this edge either. And I also couldn't include this edge. Now, the next edge that I should consider is this edge connecting G and H. But if I include this edge, it will lead to a closed figure. The closed figure will be G, E, F, I, H, G. So if I include this, it will lead to this closed figure, which will lead to a cycle. So I cannot include this edge. I cannot include it. Now the next edge that I should consider is the edge having a weight of 14. And this is my last edge. Now if I include this edge, if I include this, it will lead to a closed figure, right? A, E, G, D, A. So I cannot include this edge either. So the last few edges, none of were included. None of the edges were included. So in steps 13 and 14, we couldn't include any more edges. And now we have a connected graph, right? we have a connected graph, which is a minimum spanning tree. And what is the total cost? The total cost of the minimum spanning tree will come out to be, just sum up the weights. The weights that I will consider are 2, this one, 3, the next one is 4, the next one is 5, the next one that I should consider is of course 6, the next one is 7, the next one is, I think after 7 I have 9, so it's 9, and the last one is 10. Last one is 10. As you can see, I have considered all the edges, right? Just let me verify. Yeah, I've considered all the edges. Now, if you sum it up, what will you get? 2 plus 3, 5, 5 plus 4, 9, plus 5, 14, 20, 27, 36, 46. So, the total sum of weights is 46. Okay. Now, if you apply Prim's algorithm on this, you will get the same result. Let's just give you a head start on how to apply Prim's on this. Let me just show you. I'll do it quickly. Okay, I'll just trace over this figure. I'll start with the edge having the least weight. So I'll consider this edge, right? Now, the edges that I can consider are those incident on G and E. So which are the edges that I have? This edge connecting E and A, the edge connecting G and H, the edge connecting G and D. Now, out of these three edges, which has the least weight? The edge connecting G and D has the least weight. So I'll include it. I'll include this edge. Now, which are the edges under consideration? This one, this one, this one, and this one. Now, out of these, I can see that 7 has the least weight, so I'll include it. So I'll include 7. Now, which are the edges under consideration? I have this edge, 12. I have this edge, 13. I have this edge, 11. I have this edge, 3. Now, out of these edges, which one should I add? In fact, I should have added 3 before, right? I should have added 3. And then I think I should have added 4. Yes, I should have added 4. And then I should have added 6 and 7. Yeah, I think I just made one slight mistake. Anyway, all these edges will be there as it is. Now, after this, the next edge that I should consider is this one. 5 should be there, right? Now, at every step, you can see that the graph is still connected. And followed by this, we will have the edge with the next weight, which is 9, right? 9 has the least weight. And the next edge that we should consider out of the remaining edges, which is the edge that we should consider? See, out of the remaining edges, we should consider this edge. We should consider the edge 10, right? Now, if you observe the graph, that how many edges have we added? 1, 2, 3, 4, 5, 6, 7, 8. Right? And how many vertices are there? 3, 6, 9. We have added 8 edges, so we can stop. Now, it is exactly the same. The part I've traced out using red is same as the minimum spanning tree that we have here. So that means that the minimum spanning tree that we got using Kruskal is same as the one we would get using Prim's. So this just proves that the minimum spanning tree is always unique, irrespective of the algorithm applied, provided the edge weights are all unique. Okay, I'll just go through this once. I hope you understood. I started off with 2. Now the edges that I could consider were this one, 3, and then I had 6 to consider. I had 4, so I added 3, and then I added again 4, and after 4 I added 5. Now after 5 I had the option of adding, you can see I had the option of adding 6, so I added 6, which led to 7, and then I had the option, because of adding 4, I had the option of adding 8. So what I did was, instead of going for 8, so what we did was, instead of adding 8, I think we added 9, which was correct, and then we added 10. Yeah. Okay, so now we'll move on to the next one. Okay, let's continue. Now here, what we can see is we have been given a graph, and we have to find the minimum spanning tree using Prim's algorithm. Again, we'll show every step. So at step 1, so Prim's algorithm involves starting with the edge having the least weight. So that is this edge. So I'll consider this edge connecting A and B, and it has a weight of 1. Okay, so this part is done. This edge has been considered, so this is done. Now the edges that are under consideration, the edges, if you consider, what are the edges that we have? I'll consider only the edges incident on A and B. That means I have 5, I have 4, I have 7, I have 8, right? See, 7, 8, 4, 1 has already been taken, and from A I have 5. So out of all these edges, which has the least weight? The edge connecting B and C has a weight of 4, so I'll add that. So I'll add the edge connecting B and C. So that has a weight of 4. Now this was step number 2. This was step number 2. Now how many vertices do I have? I have vertices 1, 2, 3, 4, 5, 6, 7. So how many edges do I need to add? I need to add 6 edges. That means I'll go only up to step 6. Okay. Now after this 4, which edge should I consider? Now see, the edges which are under consideration are, okay, which edge has just been excluded? The edge, this has been excluded right now. Now the edges under consideration are this one, 2, the one, 5, this one, 6, there is 7, and there is 8. So out of all these edges, 2 has the least weight. So we'll include it. So we'll include this edge, which has a weight of 2, and this is my step number 3. So since I've included the edge, I'll just cross it out so that you can understand. Now, the next edge that I should consider, now what are the edges under consideration? I have this edge 9, this one 3, and there is this 5, and there is 7, and there is 8. Considering only the edges incident on the vertices that I currently have in my minimum spanning tree. In my minimum spanning tree, I currently have A, B, C, and F. So the edges incident on these 4 vertices are under consideration. So I can see that from F to E, there is this edge, right? There is this edge from F to E. So I can consider this, right? So let me consider this edge connecting F and E. So if I include it, so this will be my step 4. So this will be my step 4, and it has a weight of 3. So this is done. So that takes care of this edge. Now the next edge that I should consider, so what are my possible options? So A to C. See, A to C is an option, but I'll not choose A to C. See, I'll not choose A to C. Why? I'll not choose A to C because, see, I have already added vertex A and vertex C. I've already added vertex A and vertex C. So I'll not choose any edge which will again give rise to the same vertices. See, there is this edge connecting A and C. Like I said, we will not be checking for cycle. Don't think that I am excluding this edge because it leads to a cycle. No. In Prim's algorithm, we are not required to check for cycles. At every step, we are adding new vertices. But if I include this edge 5, am I adding a new vertex? I'm not. Because by including this edge connecting A and C, I am considering only the vertices which have already been added. So by adding this edge, no new vertex is being added in my graph. So I cannot add this edge. I cannot add the edge 5. I cannot add the edge 5. That is the reason why. Not because it leads to a cycle. For Prim's algorithm, we do not have to check for cycles. We have to add new vertices at every step. So we'll add an edge which will lead to a new vertex. Anyway, now I hope you have understood that point, the reason for not including this. Now the next edge that we can consider, the next edge with the least weight is 6. See, out of all the edges that we have, I have this edge with a weight 6, so I can add it because it will lead to a new vertex D. So let me just add this edge 6, right? So how many edges do I have I added now? 1, 2, 3, 4, 5. I've added 5 edges already. So I've covered 5 steps. Now the last step, which edge should I add? I should be looking to add a vertex, right? So I should add an edge such that it leads to a new vertex. Now the only vertex that is missing in my minimum spanning tree is vertex G. So if I add vertex G, which edge will have the least weight? See, this edge connecting E and G has the least weight. So I'll add vertex G using the least weight of 10. Now I've added 6 edges, right? I've added 1, 2, 3, 4, 5, 6 edges, and I can stop the procedure now. And what is the total cost? What is the total cost of my minimum spanning tree? The total cost comes out to be 1 plus 2 plus 3 plus 4 plus 6. So that's 1, 2, 3, 4, 5 plus 10. So it comes out to be 1 plus 2, 3, 6, 10, 16, 26. So it comes out to be 26. Now, had I applied Kruskal's algorithm, I would have got the same result. I'll show you. See, I'll just go quickly, okay? So the first thing that I do is I need to have all my vertices. So I have A, I have B, I have C, I have D, I have E, and I have G, and I have F. So these are all my vertices. Now I'll start with the vertex having the least weight, and I'll keep on checking for cycles. So this one has the least weight, so I add it 1. The next smallest weight is that of 2, and it does not lead to a cycle, so I'll add it 2. Since all edge weights are unique in this graph, these two minimum spanning trees will also be the same. Now the next edge weight to consider is the edge weight having a value of 3. See this one, and it has the least weight, so I'll add it, and does not lead to a cycle either. Now the next one to consider is 4. If I consider 4 and if I add it, will it lead to a cycle? See, if I add this, it's not leading to a cycle, right? There is no closed figure, so it does not lead to a cycle. The next edge weight to consider is the edge connecting A and C. But if I add this edge, it will lead to a cycle, so I cannot add it. Next edge weight to consider is 6. See, if I add 6, if I add this one, the edge weight 6. So this was also added, right? Here it was added. I should have crossed it out anyway. So if I add this edge, will it lead to a cycle? Of course not. So I'll add it, 6. The next edge weight to consider is 7. Now if I add 7, it will lead to a closed figure, B, E, G, C, B. That's why I cannot add it. Now the next edge weight to consider is 8. If I add 8, it will lead to this triangular closed figure, B, D, C, B. So I cannot add it. The next edge weight to consider is 9. If I add 9, then I'll get another closed figure, C, D, F, C. So I cannot include it. The next edge weight to consider is 10. So I'll add it because it's not leading to a closed figure. The next edge weight to consider is 12. But if I add 12 connecting G and F, it will lead to a closed figure, E, F, G, E. As a result, I'll not add it. Now if you see this spanning tree and this minimum spanning tree, it's exactly the same because edge weights are all unique. And the total cost also will come out to be 26. So I hope you have understood this point. Okay. Now I just want to take up a last example. Again, now what is the difference? You might be wondering, the structure of both graphs is exactly the same, but how do they differ? They differ in the fact that edge weights are repeated. You may be given graphs where edge weights are repeated, and it's not necessary for all edge weights having the minimum value to be included in your final minimum spanning tree. And I'll prove this point. See, what is the edge having the least weight? The edge with the least weight is 1, and there are 4 edges having the weight 1. But you will observe that at the end of our procedure, not all the edges with weight 1 will be included in the final minimum spanning tree. I'll show you how. So this is using Prim's algorithm. So let's see how it's done. So I'll start with my step 1. My step 1 will be involving including the edge having the least weight. Now see, I have so many options. I can include the edge connecting A and B. I can include the edge connecting A and C. I can include the edge connecting B and C. I can include the edge connecting C and D. So there are many options, right? I can choose any one. Because of this, because of repetition in edge weights, you will see that the minimum spanning tree will not be unique. I'll show you 2 ways to go about it. So let me add this edge, A to B. So I'll just go quickly over it, okay? You show the steps separately in your copy. Now the next edge weight to consider, which will lead to a new vertex, is this one, B to C, or I can even consider A to C. Let me consider B to C, okay? So I'll add this edge, okay? Now the next edge weight to consider, see, I cannot consider A to C. Why? Because if I add this edge, it will not lead to any new vertex. But if I add this edge connecting C and D, it will lead to the formation of a new vertex, which is vertex D. So I'll add it. Now the next edge weight to consider is edge 2. So if I add edge 2, it will lead to a new vertex F. Now The next edge weight to consider is, if you observe carefully, is the edge weight 4. But if I add this edge weight of 4 connecting B and D, it's not leading to any new vertex. So I cannot add it. See, if I add this edge, see, I won't say that it's leading to a cycle, that's why I'm not adding it. I'm not adding it because it is not leading to any new vertex. If I connect these two vertices, I'll not get any new vertex in my minimum spanning tree. My minimum spanning tree using Prim's algorithm should be formed in such a way that it leads to a new vertex at every step. Now, adding this edge connecting B and D will not lead to the formation of any new vertex. That's why I'll not include it. Now, the next edge weight to consider is 5. So, if I add this edge connecting D and E, it will lead to a new vertex it will lead to a new vertex E with an edge weight of 5 connecting it with D. Now, the next edge weight to consider is 6. But if I add this, it will not lead to a new vertex, because connecting E and F would simply mean connecting two vertices which already exist in my graph. So I cannot consider this. Now, the next edge to consider is 7. So if I connect B and E, it won't make any difference. It will not lead to any new vertex. So I'll not consider the edge 7. Now, the next edge to consider is, if I'm not mistaken, it's 10. So if I add 10, it will lead to a new vertex G. Now, how many edges have I added? 1, 2, 3, 4, 5, 6. And how many vertices are there? 1, 2, 3, 4, 5, 6, 7. See, 1, 2, 3, 4, 5, 6, 7. I can add a maximum of 6 edges, right? I can add a maximum of 6 edges if I don't want any cycles in my graph. And that is the terminating condition of Prim's algorithm. You'll keep on adding n minus 1 edges. You'll keep on adding edges till you reach the value of n minus 1, where n denotes the number of vertices. So in this case, you could add a maximum of 6 edges, and I've added 6 edges, so I'll stop. Now, this is my minimum spanning tree. What is the total cost? The total cost will come out to be, if you just add up the edges, what will you get? 1 plus 1, 2, 2 plus 1, 3, plus 2, 5, plus 5, 10, plus 10, 20. So you will get a total cost of 20. Now, the total cost will always remain the same. You can get multiple spanning trees. I'll show you another one. I'll show you another spanning tree. You can get multiple spanning trees. That means the structure will differ, but the total cost will remain the same. If there are repetition in edge weights, when you have edge weights repeating, then the structure of the minimum spanning tree no longer remains unique, but the total cost will always remain unique. And if the edge weights are all unique, the structure of the minimum spanning tree remains unique, and so does the total cost. So I'll show you another structure. Another possible combination could have been, let's say you started off with the connection between A and C. Very much possible. You'll start off with the edge having the least weight. So A to C has a weight of 1. That's possible. Now let's say you consider the edge, this one, the edge connecting C and D, because it leads to a new vertex. So you add it. Now the next vertex that you will consider is B, right? See, B, you'll consider this edge because it has the least weight, and it's also leading to a new vertex. So if I add this one, it's perfectly fine because it's leading to a new vertex. Now I cannot consider this edge anymore. I cannot consider the edge between A to B, which I did in the first case. Why? Because if I add this edge, it will not lead to any new vertex. So I'll not consider it. Now the next edge that I can consider is the edge connecting D and F. Now that one is very much allowed because it will lead to a new vertex. Now the next edge to consider is the edge having a weight 4. But if I add this edge connecting B and D, it will not lead to any new vertex. So I'll not consider it. The next edge that I have in mind is 5. So if I consider this edge connecting D and E, it's allowed. Why? Because adding this edge is leading to a new vertex E in my minimum spanning tree formed so far. The next edge is 6. If I consider this edge connecting E and F, this edge with weight 6, if I consider it, it will not be right. Why? Because if I add this edge connecting E and F, it will lead to no new vertex. I'll be simply adding, or I'll simply be joining 2 existing vertices of my minimum spanning tree. So I'll not consider 6. The next edge to consider is 10. If I add this edge connecting E and G, it's allowed. Why? Because this edge is leading to a new vertex G. Now see, how many edges do I have? 1, 2, 3, 4, 5, 6. And how many vertices do I have? 7. So I've added 6 edges. So I can stop the procedure. And what is the total cost that I get? I get 1 plus 1, 2 plus 1, 3 plus 5, 8 plus 2, 10 plus 10, 20. So the total cost again comes out to be 20. See, the total cost in both cases remain the same, but the minimum spanning tree differs. The minimum spanning tree differs. So this is how you can get multiple spanning trees if edge weights are repeated. So I'll just, before I finish it off, I want to draw your attention to this part. If you remember, maybe I got a bit stuck in this graph when I tried to show it to you using Prim's algorithm. What did I say? You start off with the least weight. So you considered this one, 2. Then your options are 3, 4, 14. There are a number of options. You will take this one. Why? Because it has the least weight and it also leads to a new vertex. Then your next option should be 4, because if you use it, it will lead to a new vertex. Your next option should be 5, because it's the least weight and it leads to a new vertex. Your next option should be 6, because it is the least weight and it leads to a new vertex. Next option should be 7. It's of least weight and it leads to a new vertex. Your next option cannot be 8. Why? Because C and F have already been added to your minimum spanning tree, and if you add this edge, it will not lead to a new vertex. See, adding this edge connecting C and F, which have already been added to my minimum spanning tree, will not lead to any new vertex. That's why I cannot consider this edge connecting C and F. That's why I decided to discard it in my Prim's approach. Next edge to consider is 9. I'll consider it. Why? I'll add it. Why? Because it is leading to a new vertex I. The next edge to consider is 10. I should add it. Why? Because it is leading to a new vertex H and it's also of the least weight. The next edge to consider is 11, but I'll no longer check. Why? Because how many edges have I added? 1, 2, 3, 4, 5, 6, 7, 8. I've added 8 edges. And how many vertices are there? 3, 6, 9. I'm supposed to add a maximum of n minus 1 edges. That means 8 edges in this case. That's why I stopped the procedure. Okay. So I just wanted to make things absolutely clear. I wanted to clarify this point because I thought I got maybe a bit stuck while explaining this using the Prim's approach. So I hope the algorithms are absolutely clear. If you have any doubts, please feel free to leave it in the comment section below. I'll get back to you. Thank you so much.